Hello everyone, my name is Adamos Christou and I'm a researcher at the University of Glasgow, where I'm a member of the Bendable Electronics and Sensing Technologies group. Today, I will present to you our work on touch interactive 3D surfaces. I will begin this presentation by talking about touch-based interaction through electronics, after which I will present the design and implementation of a 3D touch surface that we have developed, which is based on the frustrated total internal reflection principle. I will then discuss the use of this device for an interactive pseudo-holographic display before moving on to conclusions. Touch-based interaction can be regarded as the most effective and direct method for interaction with the real world. It gives us the ability to manipulate objects and understand their physical properties. For example, how soft or how rough something is. As a result of this, touch interaction has been widely used to interact with electronics. This is achieved with different types of touch sensors, which are integrated as an electronic skin. One of the simplest implementations of eSkin is the touchscreen interface that we find in smartphones and tablets nowadays. If we think about the touch interfaces that we commonly use, most of them are planar. Also, they usually have a display underneath, which provides visual feedback to the touch input. The restriction to planar interfaces is partly because of the available technologies for manufacturing the touch sensors and displays. However, with recent advancements in the field of flexible electronics, deformable sensors and displays are now being made. At the other end of the spectrum, there exist other technologies which enable touch sensing in 3D space through mid-air gesture recognition. This is achieved by optically detecting hand motion or through special gloves and handheld controllers. However, these methods are often cumbersome to use and also come with a cost disadvantage. For this work, we are presenting a new approach which brings touch sensing out of the 2D plane, while also preserving some of the advantages of the simpler planar approaches. We refer to our approach as 3D touch surface, and it is based on the frustrated total internal reflection principle. For FTIR touch sensing, we begin with a waveguide, in this case an acrylic sheet, with infrared LEDs placed at the edges. With the angle of incidence greater than the critical angle, the emitted infrared light is totally reflected and remains within the waveguide. However, when we touch the panel, and due to our fingers having greater refractive index compared to air, part of the light escapes from the waveguide. An infrared camera facing the panel is used to detect the escaping light. Implementations of FTIR touch sensing have been reported since 2005, but all have been two-dimensional. For our approach, we are presenting a 3D implementation of FTIR. To achieve this, we replace the flat waveguide with a four-sided acrylic pyramid, with infrared LEDs placed around the bottom edge. Acrylic is one of the most suitable materials for this application, as it has high light transmission and no infrared absorption. To detect the infrared light, we are using a webcam, which was modified by adding a bandpass filter in the lens to filter out visible light. We are using image processing algorithms to process and condition the images that we receive from the camera. As you can see from the images on the right, the points of touch appear as white blobs on the black background. Through software, we are able to detect single and even multiple touch inputs on all sides of the pyramid. Additionally, we can recognize gestures, such as swipe and pinch to zoom. To demonstrate the potential of the 3D touch surface, we paired it with a pseudo holographic display. To do this, an LCD screen is placed above the pyramid facing downwards. The images displayed on the screen get reflected on the sides of the pyramid, and as a result, we can see virtual objects which appear to be floating inside the pyramid. This system is based on the Pepper's Ghost projection scheme. The pyramid was designed with this application in mind, and the panels form a 45-degree angle with the screen so that we get optimal visual results when looking at the pyramid horizontally. As with the planar touch interfaces with integrated displays, the user can use a 3D touch surface to interact with whatever is being displayed on the screen. The touch inputs are mapped on the sides of the pyramid, and from there onto the corresponding points on the virtual object. Based on the user's input, the 3D model of the object is transformed and rendered in real time to be projected on the screen. When considering the use of FTIR for 3D touch surfaces, and with the interactive pseudo-holographic display application in mind, the technology does have some advantages. Compared to other sensing technologies, such as resistive or capacitive, the single-layer interface of the FTIR does not compromise transparency, something that is important for this type of displays. Another important advantage is the simple implementation, which reduces the cost and also means that the system can be scaled up easily. FTIR also has multi-touch capability with fast response. It is not affected by moisture or electromagnetic interference and can be used while wearing gloves. We can also take a look at other modes of interaction with 3D displays and virtual objects, which are currently used with pseudo-holographic displays, volumetric displays, and VR headsets. Simpler methods include physical controls such as buttons and joysticks, and conventional 2D touchscreens. More advanced methods include the mid-air gesture recognition approaches that we talked about previously. We believe that the 3D touch surface sits right between the two categories. It offers a more immersive experience than the simpler approaches by giving the illusion of directly touching the virtual object. When compared to the more immersive mid-air gesture sensing, the 3D touch surface approach can be much easier to use, as it has a shallower learning curve. This is quite important when people are using it for the first time. Because of these advantages, the 3D touch surface paired with a 3D display could find applications in places such as schools, museums, exhibitions, and retail stores. To conclude, I have presented the design and implementation of a 3D touch surface based on the frustrated total internal reflection principle. I have demonstrated an application of the 3D touch surface for a touch interactive pseudo-holographic display. And finally, I have discussed the merits of the proposed system and potential uses. I would like to thank the Engineering and Physical Sciences Research Council for supporting this project, as well as the members of the Bendable Electronics and Sensing Technologies Group for their help and support. Thank you for attending this presentation. Feel free to visit our group's social channels for more information on this work, as well as other projects.